Okay, so let's talk about 3 examples of electrochemical cells. Okay, so the first will be the lead-acid battery. And the basic structure of the lead-acid battery is that we have one electrode is lead, one electrode is lead oxide, and the electrolyte in this case is sulfuric acid. Okay, and these are in some cell in your car and other places. And then we have them connected by a wire, right? And typically the electrons are moving from the lead to the lead oxide, right? So we have, this is the anode, and this is the cathode. Okay. So the reactions in the lead-acid battery, the anode reaction is that we have, so here's Pb, which is a solid lead, reacting with the SO4 part of the sulfuric acid, which is aqueous, and it's converting to PbSO4, which is a solid, and 2 electrons. Okay, so that's depositing off. And then at the cathode, we have, so let's do that in green. We have lead oxide, which is a solid, plus lead, which is a solid, plus 2 SO4, which are aqueous, and charge 2 minus, plus 4 hydrogens, which are aqueous, because that's part of the part of what's dissolved into the solution, and those are going to 2 PbSO4 solid plus 2 waters. Okay. So, no. That's going to sorry. So we have PbO2 plus 2 SO4, sorry. I've been combining my reactions. So we have the lead oxide combining with the SO4 part of the sulfuric acid and 2 electrons. And those are becoming PbSO4, okay, plus 2H2O. Okay, apologies. There we go. Okay, right, the lead oxide is combining with the sulfuric part of the sulfuric acid and 2 electrons that come up through the wire to make PbSO4, which will deposit on the lead oxide electrode and release 2 water. Okay, so overall, we could combine these two. And what we have is that PbO2 solid plus Pb solid. So now we're just adding the 2 reactions, plus 2 SO4, 2 negative, which is aqueous, plus the 4 hydrogen ions, which are also aqueous, are going to 2 PbSO4, which is a solid that'll deposit out, plus 2 H2Os. Okay, and we can calculate the free energies or look up the free energies of formation of all these various compounds and figure out what the change in free energy per mole of the cell is. And in this case, it's going to be minus 385 kilojoules per mole. So this is a spontaneous reaction. So this is actually a galvanic cell. Okay. And the difference in voltage of the cell can be calculated, and that's 1.995 volts. Okay. So that's our first example. So the second example is, let's say we wanted to use such a cell to create hydrogen, to split water. So we could use hydrogen, let's say, to run a fuel cell. So we could make similar, so this is 1. 2 is going to be splitting water. So here we're going to put at the anode a reaction where we take water and convert it to a half O2, which is a gas, plus 2H plus, which will dissolve aqueously in solution, plus 2 electrons. And the cathode, in that case, would be take the 2 dissolved hydrogen atoms plus 2 electrons and make hydrogen gas. So the overall reaction in such a cell would be essentially that you're just taking H2O, which is of course a liquid, and turning it into hydrogen gas plus oxygen gas, right? So here, if we calculated delta G, the change in the Gibbs free energy, that would be equal to 237 kilojoules per mole. So this is not spontaneous. So this kind of reaction would be an electrolytic cell. And the change in difference in voltage would have to be greater than or equal to 1.229 volts. Okay, so these are sort of two cases in point, the lead acid battery and the electrolytic cell for splitting water. A third case that might be sort of between the two of these would be 2 copper electrodes in copper sulfate Cu solution. So here we would have these are both copper, and we'd put them in this CuSO4 solution, this electrolyte. Now in this case, obviously, we're doing the same thing no matter which way we run the current. So in this case, at the anode, we have copper, solid copper, going to copper 2 plus, which is aqueous, plus 2 electrons. And at the cathode, we have copper 2 plus, aqueous, plus 2 electrons going to copper, just the opposite of the above. And so there's really no overall reaction, so delta G is 0. No overall reaction. But we could run this in either direction by hooking a battery up to it one way or the other and cause copper to precipitate out on one electrode or the other. So the voltage applied in this case determines the direction of the reaction. Okay, so these are 3 sort of limiting cases of different kinds of electrochemical cells.